Everything we know about the universe is just a tiny fragment of a grand mystery. Myriads of stars, galaxies stretching billions of light years, are just the tip of the iceberg. Beyond our understanding, beyond the event horizon, lie unexplored worlds and phenomena that could overturn our concepts of the cosmos. Every new mission, every telescope launch is a step into the unknown, revealing ever more secrets. But what if what we see is just an illusion? What if beyond the visible boundary lies something so grand and incomprehensible that our minds are simply not prepared to grasp it? We embark on a journey where the answers may be even more mysterious than the questions. What secrets lie beyond the universe we know? Could there be another reality, different laws of physics, other forms of life? Are we ready for discoveries that could change our understanding of time and space? What truly lies behind the veil of cosmic unknowns? If you're as intrigued by these questions as we are, make sure to hit like and subscribe to our channel. Join us as we venture into the mysteries of the universe and uncover what lies beyond the stars. Our universe is an immense space filled with mysteries and wonders. It emerged as a result of the self-evolution of matter, specifically due to fluctuations in the inflaton field. Its vastness is awe-inspiring and evokes reverence in anyone trying to grasp its scale. Understanding the scale of the universe is the first and most crucial dive into cosmic space, giving us insight into how small our world is compared to the boundless expanse of the cosmos. According to calculations by an international team of scientists, our universe is expected to last at least another 140 billion years. The observable universe stretches about 93 billion light-years in diameter. This distance is almost impossible to conceive, as 1 light-year is the distance light travels in 1 Earth year at a speed of 299,792 kilometers per second. In more familiar terms, this is roughly 9.46 trillion kilometers. Interestingly, most of this vast space is filled with emptiness, with sparse islands of matter such as galaxies, stars, and planets. Despite its colossal size, the observable universe is only a part of a broader reality that science has yet to fully understand. Currently, scientists estimate that the universe contains about 2 trillion galaxies and around 10 circumflex 24 stars, more than the number of grains of sand on all the beaches on Earth. These immense scales not only inspire awe, but also pose many questions. How did the universe become what it is today? What lies beyond the observable part? At what scale might we discover new physical laws or even parallel universes? Galaxies, the fundamental building blocks of the universe, are distributed across space in complex and diverse structures. Their arrangement is not random and follows specific laws, forming the large-scale structure of the universe. They have a spherical shape and contain tens of thousands of galaxies, usually elliptical or lenticular in form. At the center are 1 or 2 giant elliptical star systems. One of the most remarkable aspects of this arrangement is the existence of large cosmic voids. A major void can stretch over hundreds of millions of light-years and contain extremely low galaxy density. With a diameter of about 330 million light-years, it is one of the largest and most well-known in the cosmos. The distribution of stellar systems across space forms grand and complex structures, which are key components of the large-scale universe. Recent research by Estonian astrophysicists Y. Einasto, A. Saar, M. Yivar, and others, as well as American specialists P. Peebles, O. Gregory, and L. Thompson, has shown that the largest scale inhomogeneities in the distribution of galaxies exhibit a cellular structure. The walls of these cells contain many galaxies and raise questions about the nature and other fundamental aspects of the universe that require further research and observation. So in which cosmic structure is our home galaxy? The Milky Way, located. The local group of galaxies is a small cluster that contains our Milky Way. This cosmic ensemble includes over 54 galaxies within a radius of about 10 million light-years. The main members of the local group are 3 large spiral galaxies: the Milky Way, Andromeda, and Triangulum, or M33. The Milky Way, with a diameter of about 100,000 light-years, is one of the most massive in this group. It contains approximately 400 billion stars, numerous planetary systems, and other cosmic objects such as nebulae and star clusters. Our nearest neighbors are the dwarf galaxy in the Large Magellanic Cloud and in the Small Magellanic Cloud, located about 25,000 and 200,000 light-years away respectively. Andromeda, M31, is the largest galaxy in the local group. It is located approximately 2.5 million light-years from the Milky Way and has a diameter of about 220,000 light-years. Andromeda contains around 1 trillion stars, making it the largest member of our local cosmic environment. In the future, in about 4.5 billion years, Andromeda and the Milky Way are expected to collide and merge, forming a new stellar system. An interesting aspect of the local group is the Triangulum Galaxy, M33, which is about 3 million light-years from Earth and has a diameter of around 60,000 light-years. M33, with a population of 40 billion stars, is also a spiral galaxy, but smaller compared to the Milky Way and Andromeda. This group also includes many dwarf star systems, such as the Leo 1 dwarf galaxy and the Sculptor dwarf galaxy. They generally have a diameter of less than 10,000 light-years and contain far fewer stars compared to the larger members of the group. Many of them orbit around more massive galaxies, acting as their satellites. A central question in this cosmic group is what lies within the cores of these galaxies. Could there be black holes significantly more massive than our Sun at their centers? These are questions that drive further research and new experiments. Interactions between galaxies in the local group occur under the influence of gravitational forces. Such interactions can lead to the exchange of material, the formation of new star systems, and even mergers. An example of such interaction is the dwarf galaxy M32, a satellite of Andromeda, which shows signs of tidal effects from its larger neighbor. As a small part of the cosmic web, this group serves as a unique laboratory for studying the evolution of galaxies and their interactions. Studying them helps astronomers better understand processes occurring on the scale of the universe and learn more about our own galactic home. Superclusters of galaxies represent some of the grandest and most massive structures in the universe. They consist of numerous galaxy clusters connected in vast networks that stretch hundreds of millions of light-years. These systems form under the influence of gravity and are key components of the large-scale structure of the cosmos. One of the most well-known superclusters is Laniakea, which includes our local group of galaxies. Laniakea spans 520 million light-years and contains about 100,000 galaxies. Discovered in 2014, its name, which means immeasurable heavens in Hawaiian, symbolizes its vast size and significance in the cosmic scale. Within Laniakea is the Virgo supercluster, which consists of thousands of galaxies and has a diameter of about 110 million light-years. It is one of the most thoroughly studied regions of space due to its relative proximity to Earth. Typically, superclusters contain numerous galaxy clusters. One of the densest is the Coma cluster, located in the Virgo supercluster, approximately 320 million light-years from Earth and containing over 1,000 galaxies. It spans about 20 million light-years and serves as a vivid example of how galaxies can cluster under gravitational forces. Another impressive supercluster is the Shapley supercluster, situated about 650 million light-years away, comprising thousands of galaxies grouped into several clusters and with a size of around 500 million light-years. The Shapley supercluster is one of the most massive structures known. These constructions are crucial for our understanding of cosmic processes. They provide insights into the early universe and its evolution over time, showcase the grandeur of cosmic structures, and open new horizons for research and discovery. How are these grand scales related to the concept of the cosmic web? The cosmic web is a term used to describe the large-scale structure of the universe, where galaxies and their clusters are distributed like nodes and threads in a vast web. This grand system, visible on the largest scales, results from the gravitational interaction of matter and dark matter, forming complex and extensive structures. According to cosmological modeling, over 60% of the hydrogen formed after the Big Bang collapsed to create a layer that then fragmented into cosmic filaments. These filaments connect galaxies and supply them with gas for growth, and star formation. The main components of the cosmic web are filaments, nodes, and voids. There are two primary types of filaments, cold and hot. Cold filaments contain gas at relatively low temperatures, which promotes the formation of new stars. Hot filaments, on the other hand, are filled with high-energy gas heated to millions of degrees, which slows down star formation but significantly affects the dynamics of galaxies. According to a study published in Nature Astronomy *, astronomers have recently obtained a direct image of a section of the vast cosmic web structure previously hidden in a very distant part of the universe. Previously, scientists used the Keck Observatory in Hawaii to get an indirect image of this area billions of light-years away from Earth about 8 years ago, utilizing the light from a nearby quasar. Now, astronomers have managed to capture a direct image of cosmic web filaments located 10 to 12 billion light-years away, using background light filtering from the solar system and our galaxy. As a result, they captured the light of the most intense emission in the cosmic filament region, gaseous hydrogen. This area was previously hidden from astronomers because it lies much further in the darkest corner of the universe, where it was not illuminated by galaxy clusters or quasars. Consequently, astronomers have created a three-dimensional image of this very distant region of the web. One of the most impressive examples of filaments is the CFA-2 Great Wall, discovered in 1989. This structure spans about 500 million light-years and consists of numerous galaxy clusters connected by filaments. The Hercules Corona Borealis Great Wall, discovered in 2013, stretches an incredible 10 billion light-years and is one of the largest known structures in the universe. Voids, which fill the space between filaments and nodes, also play an important role. These areas are characterized by extremely low galaxy density and can span hundreds of millions of light-years. This complex network formed under the influence of gravitational forces acting on ordinary and dark matter since the Big Bang. Dark matter is a mysterious component of the universe that, despite being invisible, plays a crucial role in the formation of galaxies and large-scale cosmic structures. Although its nature remains unknown, scientists estimate that it constitutes about 27% of the universe's mass-energy content. Dark matter interacts with ordinary matter through gravity, but does not emit, absorb, or reflect light, making it invisible to traditional astronomical observation methods. The primary evidence for its existence emerged in the mid-20th century when astronomers noticed that the orbital speeds of stars in galaxies did not match the expected values based on the visible mass of these stellar systems. Galaxies were rotating faster than could be explained by visible matter alone, suggesting the presence of additional unseen mass. Dark matter forms gravitational frameworks around which ordinary matter accumulates, creating galaxies and their clusters. These frameworks are invisible halos that contain most of the mass. For example, in a typical galaxy, dark matter may be 10 times more massive than all visible stars and gas combined. In the Milky Way, the dark matter halo extends about 300,000 light-years, significantly exceeding the diameter of the visible part of the galaxy. How does dark matter influence galaxy formation? When the universe was younger and composed of hot plasma, it began to create gravitational wells. These wells became centers where ordinary matter accumulated, cooled, and formed the first stars and galaxies. Without dark matter, the process of galaxy formation would have been much slower and less efficient. Dark matter also affects the cosmic microwave background, CMB, which is the residual radiation from the Big Bang. Fluctuations in this radiation indicate the presence and distribution of dark matter in the early universe. CMB studies conducted with space telescopes like Planck have provided crucial data on its quantity and distribution. To further understand its nature, scientists conduct various experiments both in space and on Earth. They use detectors placed deep underground to catch rare interactions between dark matter particles and ordinary matter. Additionally, particle accelerators like the Large Hadron Collider, LHC, are used to create and study particles that might constitute dark matter. Thus, dark matter remains one of the most enigmatic and fundamental components of the universe. Its role in galaxy formation and large-scale structures is key to our understanding of the cosmos. Ongoing research and observations continue to provide more data, bringing us closer to unraveling this great cosmic mystery. What do we know about the elusive nature of dark energy? Dark energy is another mysterious component of the universe that, despite its invisibility, has a profound effect on its behavior. While dark matter is responsible for the formation of galaxies and large-scale structures, dark energy is responsible for the accelerated expansion of the universe. Scientists believe it accounts for about 68% of the total mass energy of the universe, making it the dominant component. Hints of dark energy's existence emerged in the late 1990s when two independent groups of astronomers studying type Ia supernovae discovered that the universe is expanding at an accelerating rate. This discovery contradicted the prevailing theories that predicted the expansion should slow down due to gravity. Instead, the observation suggested that some unknown force is pushing galaxies apart, causing the accelerated expansion. The rate of the universe's expansion is determined by the Hubble constant, which is currently estimated to be about 70 km/s/mpc, kilometers per second per megaparsec. However, this rate has not been constant throughout the history of the universe. Before the discovery of dark energy, it was assumed that gravity was slowing down the expansion. However, observations show that about 5 billion years ago, the expansion began to accelerate, indicating the predominant influence of dark energy. The mechanism of its action remains one of the biggest mysteries in modern cosmology. One leading hypothesis is the cosmological constant, proposed by Albert Einstein in 1917 within his general theory of relativity. Alternative hypotheses include the theory of quintessence, which posits the existence of a dynamic scalar field affecting the rate of the universe's expansion. Unlike the cosmological constant, quintessence can vary over time and space, leading to a more complex model of the universe's evolution. The influence of dark energy on the structure of the cosmos is evident when observing large-scale structures such as superclusters of galaxies and the cosmic web. Dark energy stretches space, causing distances between galaxies and clusters to increase. In the future, if current trends continue, star systems will continue to drift apart, and the universe will become increasingly sparse. Various observational methods are used to study dark energy, including mapping large-scale cosmic structures, studying the cosmic microwave background radiation, and investigating type Ia supernovae. Space missions, such as the Planck satellite and the upcoming Euclid mission, provide more data, helping scientists understand the nature of this mysterious force. How is cosmological redshift related to the study of dark energy? Cosmological redshift is a phenomenon associated with the expansion of the universe, playing a crucial role in modern cosmology. As light from distant galaxies and other cosmic objects travels toward us, its waves are stretched due to the expanding space. This results in an increase in wavelength and a shift of the light toward the red part of the spectrum. This effect is called redshift and is an important tool for studying the universe. The first scientist to discover redshift was the astronomer Edwin Hubble. In 1929, he observed that the light from distant galaxies was shifted toward the red part of the spectrum, and that the extent of this shift was directly proportional to their distance from Earth. This discovery laid the foundation for Hubble's law, which states that the rate at which galaxies are receding is proportional to their distance from us. Hubble's law is expressed by the formula V equals sign d, where V is the recessional velocity, d is the distance to the galaxy, and h0 is the Hubble constant, which is currently estimated to be around 70 km/s/mpc. Redshift is classified by the magnitude z, which indicates how much the wavelength of light has changed. If lambda is the observed wavelength and L0 is the original wavelength, then z equals sign lambda LO L0. For example, if z equals sign 1, it means that the wavelength has doubled. Cosmological redshift provides valuable information about the structure and evolution of the universe. It allows scientists to measure distances to distant galaxies and study their speeds, helping to determine the rate of the universe's expansion at different epochs. For instance, studying galaxies with high values of z, such as z equals sign 6 or higher, provides a glimpse into the early stages of the cosmos when the universe was less than 1 billion years old. Moreover, redshift is used to create three-dimensional maps of galaxy distribution. Modern sky surveys, such as the Sloan Digital Sky Survey, SDSS, collect data on millions of galaxies and their redshifts, creating maps that display the large-scale structure of the universe. Interestingly, redshift is not limited to galaxies. It is also observed in the emission of cosmic microwave background, CMB radiation, which is a remnant of the Big Bang. It has a redshift of about Z equals sine 1100, corresponding to a time when the universe was about 380,000 years old. Cosmological redshift also plays an important role in calibrating cosmic distances. Type Ia supernovae, used as standard candles, allow for the measurement of distances to distant galaxies and the estimation of their redshifts. How are measurements of distances to distant galaxies using Type Ia supernovae related to determining the age of the universe? One of the primary methods for accurately estimating the age of the universe is the study of cosmic microwave background, CMB, radiation. This radiation is a relic of the Big Bang, preserved to this day and permeating all of space. Cosmic microwave background radiation was first detected in 1965 by Arno Penzias and Robert Wilson. It has a temperature of about 2.7 Kelvin and is distributed across the entire sky. Interestingly, this discovery was made by accident. The scientists used a microwave telescope and consistently detected an additional signal that did not disappear regardless of where they pointed the antenna. Initially, they suspected the signal might be due to a malfunction of the telescope or even pigeon droppings on the antenna. However, they later realized they were the first to detect cosmic microwave background radiation, the existence of which had been predicted by Big Bang theory. For their discovery, Penzias and Wilson used the 15-meter Holmdel-Horn antenna, which subsequently became famous for this significant finding. They were awarded the Nobel Prize for their achievement. This information is adapted from the conversation under a Creative Commons license. Modern space missions, such as the Planck Space Telescope, have provided the most detailed maps of the CMB, allowing scientists to make precise measurements of its characteristics. The Planck data, published in 2018, indicated that the age of the universe is approximately 13.8 billion years. This result is based on measurements of small temperature fluctuations in the CMB, which reflect the density and composition of the early universe. One of the key parameters used to determine the age of the universe is the omega parameter, which characterizes the density of various components of the universe: ordinary matter, dark matter, and dark energy. According to Planck data, the overall density of the universe is close to the critical density, omega 1, indicating a flat geometry of the universe. Additional methods used to estimate the age of the universe include observations of star clusters and white dwarfs. For example, measurements of the age of the oldest star clusters, such as globular clusters, suggest an age of about 13 billion years, consistent with estimates from the CMB. Studies of white dwarfs, the final stages of stellar evolution, also support these estimates. How does the age of the universe relate to its evolution? Observations show that within a few 100 million years after the Big Bang, the first stars and galaxies began to form. The period known as the reionization epoch occurred about 13 billion years ago, when ultraviolet radiation from the first stars and galaxies ionized hydrogen in the intergalactic space. The age of the universe, as determined from cosmic microwave background observations, is approximately 13.8 billion years. This result is based on data about temperature fluctuations in the CMB, matter density, and the rate of expansion of the universe. Ongoing improvements in observational methods and analysis continue to refine these estimates, bringing us closer to understanding the origin and evolution of our cosmos. The evolution of the universe is a remarkable story, encompassing a series of key stages and events, each contributing to the formation of the present cosmic structure. The initial state of the universe after the Big Bang was characterized by extremely high temperatures and densities. During the first trillionth of a second, the universe underwent a period of inflation, expanding at an incredible rate and growing in size by several orders of magnitude. This stage contributed to making the space more homogeneous and isotropic. Within seconds after the Big Bang, the temperature decreased to a level where elementary particles, such as protons and neutrons, began to form. About 3 minutes later, nucleosynthesis occurred, resulting in the formation of the first light elements: hydrogen, helium, and lithium. Hydrogen made up about 75% of the mass, and helium about 25%. Approximately 380,000 years after the Big Bang, the temperature dropped to about 3,000 Kelvin, allowing electrons to combine with nuclei to form neutral atoms. This process, known as recombination, made the universe transparent to light, which we observe today as the CMB. The next key stage in the universe's evolution is the era of dark ages, which lasted until the formation of the first stars and galaxies. Within a few 100 million years after the Big Bang, the first stars began to form, ionizing the surrounding hydrogen and initiating the epoch of reionization. This process ended around 1 billion years later. The first galaxies and clusters began to form within the first few billion years after the Big Bang. Gravitational interactions between dark matter and ordinary matter led to the formation of large structures such as galaxies and galaxy clusters. The Milky Way began forming about 10 billion years ago. Around 4.6 billion years ago, the solar system, including Earth, formed. Conditions on our planet became favorable for the emergence of life, with the first microorganisms appearing around 3.8 billion years ago. The development of life on Earth led to the evolution of complex organisms, including humans, who appeared about 200,000 years ago. The future of the cosmos remains an active area of research and speculation. Possible scenarios include the Big Rip, where accelerated expansion could lead to the destruction of all structures in the universe, or heat death, where the universe reaches a state of maximum entropy and ceases to support any processes. Inflation theory, proposed in the early 1980s, represents one of the most significant achievements in modern cosmology. This concept was developed to explain some mysterious aspects of the early universe, such as the uniformity and isotropy of the cosmic microwave background, CMB radiation, the flatness of the universe, and the absence of magnetic monopoles. According to the inflationary model, the universe underwent an extremely rapid period of exponential expansion in the first trillionth of a second after the Big Bang. This period allowed the universe to expand by many orders of magnitude, smoothing out any initial inhomogeneities and creating conditions for the formation of the large-scale structures we see today. The inflationary model proposes that during this brief time, the universe expanded by a factor of 10 circumflex 26. This process can be compared to inflating a small balloon to the size of a galaxy in a fraction of a second. How is this possible? One key aspect of the theory is the existence of an inflaton field that provided the energy for this extreme expansion. The inflaton field had a high energy density and exerted negative pressure, causing exponential expansion. Why is inflation theory so important? First of all, it explains why the universe appears so homogeneous and isotropic on large scales. Without it, any initial inhomogeneity or density fluctuation could have led to a much greater variation in temperatures and densities across different parts of the universe. Inflation smoothed out these inhomogeneities, providing a uniform distribution of matter and energy. Moreover, inflation explains why the universe is so flat. At the moment of the Big Bang, the universe could have had any geometric curvature. However, inflation expanded it so greatly that any initial curvature became nearly imperceptible. And today, we observe a universe that appears flat on large scales. The inflationary model also predicts the presence of initial quantum fluctuations that became seeds for the formation of galaxies and other large structures. During inflationary expansion, these fluctuations were stretched to cosmological scales, creating small density inhomogeneities that later led to gravitational collapse and galaxy formation. One of the first direct confirmations of the theory came from observations of the cosmic microwave background radiation by the COBE, Cosmic Background Explorer satellite, in 1992. These observations showed that the temperature of the CMB has small fluctuations consistent with the predictions of the inflationary model. Later missions, such as WMAP, Wilkinson Microwave Anisotropy Probe, and Planck, provided even more precise data confirming this model. The inflationary model also solved the problem of magnetic monopoles, hypothetical particles predicted by some theoretical models. In its absence, magnetic monopoles would have had to exist in large numbers, but inflation diluted their concentration to the point where they are practically undetectable. However, despite the successes of the concept, unresolved questions remain. For example, the nature of the inflaton field and the mechanisms that led to its end are still not fully understood. Some alternative models, such as eternal inflation and the multiverse, offer new avenues for research, but also raise new questions. This theory plays a key role in our understanding of the early stages of the universe's expansion. It explains the uniformity and flatness of the cosmos, as well as the origin of large-scale structures. How is the formation of the first stars and galaxies related to the early phases of the universe's expansion? The emergence of the first stars and galaxies represents a crucial stage in the evolution of the universe. This period, known as the cosmic dawn, marks the end of the Dark Ages and the beginning of the appearance of the first sources of light. The first stars, or population 3 stars, formed approximately 200 million years after the Big Bang. These stars were significantly more massive and hotter than modern stars. They were composed primarily of hydrogen and helium since heavier elements had not yet been synthesized. These stars could have masses ranging from several tens to hundreds of solar masses, and their lifespans were short, only a few million years. The development of the first stars began with the cooling and contraction of gas clouds. Gravity played a key role, causing the gas clouds to collapse and form dense cores that eventually became stars. How exactly did this process occur? Gravitational instabilities in the primordial gas clouds led to the formation of dense regions that continued to collapse under their own gravity. These regions gradually heated up, and when the temperature reached several million degrees Kelvin, thermonuclear reactions began, converting hydrogen into helium. Thus, the first stars were born. The appearance of the first stars had a significant impact on the surrounding environment. Their powerful ultraviolet radiation and strong stellar winds began ionizing the surrounding hydrogen. This process lasted for hundreds of millions of years and eventually led to the complete ionization of the intergalactic medium. The formation of the first galaxies began around 500 million years after the Big Bang. Galaxies formed in regions where the density of dark matter was higher, creating gravitational anchors that ordinary matter gravitated toward. The primordial galaxies were small and unstable, frequently colliding and merging with each other to form larger structures. The process of galaxy mergers played a key role in their evolution. For example, the Milky Way, one of the largest galaxies in our local group, formed through numerous mergers of smaller galaxies. How often did such mergers occur, and how did they influence the structure of galaxies? Approximately 1 billion years after the Big Bang, galaxies began to take on more organized shapes, such as spiral and elliptical forms. This process was accompanied by active star formation and the formation of the first supermassive black holes in the centers of galaxies. One of the key discoveries was the identification of galaxies that formed stars at an extremely high rate. These galaxies, known as starburst galaxies, produce stars hundreds of times faster than modern systems. This discovery allowed for a better understanding of the mechanisms of star formation and the role of galaxies in the evolution of the universe. Supernovae are also among the most powerful and dramatic events in the cosmos. These catastrophic explosions occur at the end of the life cycle of massive stars, leading to the release of enormous amounts of energy and matter into the surrounding space. Understanding the processes associated with supernovae is crucial for cosmology and the chemical evolution of galaxies. Supernovae are classified into two main types, Y and II. Type 1 supernovae occur in binary star systems, where one of the stars is a white dwarf that accretes matter from its companion until it reaches a critical mass, triggering a collapse and explosion. Type 2 supernovae occur when a massive star, having exhausted its nuclear fuel, collapses under its own gravity, leading to the explosion of its outer layers. What makes these events so significant for cosmology? First, supernovae play a key role in the chemical evolution of galaxies. During a supernova explosion, heavy elements such as carbon, oxygen, iron, and gold are synthesized and ejected into space. These elements become the building blocks for new stars, planets, and even life. For example, the iron in our blood and the calcium in our bones were created in the hearts of ancient stars and ejected into space by supernovae billions of years ago. An intriguing question is, can supernovae actually influence the emergence of life? Some scientists suggest that supernova explosions might have played a role in the formation of complex organic molecules in interstellar clouds, which in turn could have influenced the emergence of life on planets. These processes are still the subject of active research. Supernovae also serve as important tools for measuring cosmic distances. Moreover, supernovae play a role in the dynamics of galaxies. Supernova explosions create shockwaves that can compress surrounding gas clouds, initiating new cycles of star formation. These explosions can also affect the evolution of galactic disks and lead to the ejection of gas from galaxies, impacting their further evolution. One of the most famous examples of a supernova is SN 1987A, which exploded in the Large Magellanic Cloud in 1987. This event provided scientists with a unique opportunity to observe and study a supernova in detail. SN 1987A helped confirm many theoretical models and provided new data on the processes occurring during and after the explosion. Observations of supernovae are also closely linked to the search for neutrinos. Supernova explosions produce vast amounts of neutrinos, which can be detected by special detectors on Earth. These observations help scientists better understand the mechanisms of supernova explosions and the properties of neutrinos, which play an important role in fundamental physics. These powerful events continue to be the subject of active research, opening new horizons in our understanding of the cosmos and its evolution. Black holes are among the most mysterious and exotic objects in the universe. These regions of space-time with such a strong gravitational field that neither light nor matter can escape play a crucial role in cosmology and the evolution of galaxies. The concept of a black hole was first proposed by German scientist Karl Schwarzschild. According to his theory, a black hole can form at any point in space when a spherical object reaches what is known as the gravitational radius. Black holes can be classified into several types depending on their mass and origin. Primordial black holes, which could have formed shortly after the Big Bang, may range in mass from just a few grams to millions of solar masses. Supermassive black holes, which can reach billions of solar masses, are found at the centers of most large galaxies, including our own Milky Way. One key question is, how do these giants form? It is believed that supermassive black holes form through the mergers of smaller black holes and the accretion of vast amounts of gas. For example, the black hole at the center of our galaxy, Sagittarius A*, has a mass of about 4 million solar masses and likely formed through mergers and accretion over billions of years. Black holes play a central role in the evolution of galaxies. Their powerful gravitational pull influences the movement of stars and gas, shaping the structure of galactic nuclei. Active galactic nuclei, AGN, fueled by the accretion of matter onto supermassive black holes, can emit enormous amounts of energy in the form of light, X-rays, and radio waves. These emissions can significantly impact star formation processes in galaxies by heating and expelling surrounding gas. For example, Quasar 3C273, one of the first discovered, is located about 2.4 billion light-years from Earth and emits energy equivalent to 1 trillion suns. How do such objects affect their surrounding environment? The intense radiation and powerful jets resulting from the accretion of matter onto a black hole can prevent further star formation in galaxies, thus regulating their evolution. Another aspect that greatly interests scientists is the collisions and mergers of black holes. These events produce gravitational waves, which can be detected by instruments like LIGO and Virgo. For instance, In 2015, LIGO detected gravitational waves caused by the merger of two black holes with masses of about 29 and 36 solar masses. This discovery confirmed key predictions of general relativity and provided a new tool for studying the universe. Black holes may also play an important role in the formation of relativistic jets, streams of particles moving at nearly the speed of light. These jets can extend thousands of light-years from the centers of galaxies and influence the intergalactic medium by injecting energy and matter into the surrounding space. Additionally, there is a hypothesis that entire planets and even alien colonies might exist inside black holes. According to Professor Vyacheslav Dokuchayev, a researcher at the Russian Academy of Sciences Institute for Nuclear Research, certain conditions in the centers of some black holes might create a region where space and time could exist. In such a structure, bodies including photons, particles, and planets could orbit around the central singularity. The singularity of a black hole is the central region where space and time become infinite. Black holes remain critical objects for understanding the structure and evolution of galaxies, as well as for exploring the fundamental laws of physics.